Can people in Zoom hear me? Yay. Sounds good. All right. Good afternoon. How's everyone doing? Doing well? All right. Let's see what's coming up in a few days. I think, yeah, we're still in kind of a lull. Uh, this is kind of our post midterm. We're just getting slightly a bit of a break. Starting Wednesday, we're going to move into our next main topic. We've finished our first section, which is more like the basics, the Java and the asymptotics part. And then we'll move into actual data structures starting Wednesday. We may have a lab due this Friday. I think we're still trying to get that out fully. Trying to decide what we're doing in that. Other than that, I think that's it for most of the next week. We've got a few things coming up on the March 7th, but until then, there aren't really many assignments at this point. Now, before we get started, does anyone have any questions? All right, let's start. Let me just make sure that I am, yeah, I am recording. All right, so the last slide from last week was this kind of quick statement of what all the runtime or what the main theta classes you'll see kind of look like. So for example, a theta 1, that's just a constant function. It doesn't, regardless of how you change the value of n, it's not going to affect the value of function that's theta 1, or it's going to affect it minimally. If you have a theta log n, every time you double the size of the input, you're generally going to be adding 1 unit of work. Every time you add 1 to the input, you're going to not really affect the runtime too much. Theta n, if you double the size of n, then you double the size of any function that's theta n. If you add 1 to n, you're approximately adding 1 to the size of n. N squared, if you double n, you approximately quadruple the value of n squared. If you add 1 to n, you approximately increase the amount of n squared by a factor or by an amount of n. If you have something that's theta 2 to the n, doubling n is going to square the runtime. So you go from 1,000 seconds of runtime to 1,000,000 seconds of runtime in the best case scenario. And if you're adding 1 to n, then you approximately double this runtime. So these are just general rules on how you might see functions. They're not rigorously proven here. You can show why they're true with some bit more math. But these are kind of useful heuristics to see what your runtime function is. Or so what we're eventually going to lead up to is we're going to be leading up to a way to compute the runtime of a function. And normally a lot of functions that we work with, they can be reduced down to one of these two things, either a summation, which is just a sum of values from 1 to some number, or recursively defined function. Those tend to appear more with like recursion type programs. So here's an example that we showed earlier. We showed that if you add up the first n natural numbers, then you get something that's theta of n squared. The first approach we showed was this algebraic approach, where we kind of flipped one copy of f of n in this way, and we added pairwise to get a bunch of copies of n, and overall ended up at n times n plus 1 over 2. Here's kind of like the algebraic way to prove that this is true. The geometric way is arguably slightly simpler. It's not rigorous, but it does give us a general sense that it is going to be true. In effect, if you just make these blocks that are the right size and put them in this pattern, you get this triangle. And the area of the triangle is base times width divided by 2, which is just about n times n divided by 2, which evaluates to theta n squared. This isn't a full rigorous proof. It is just kind of a way to get the intuitive sense as to why it's true, but it works for most purposes. So let's start off with just a quick, let's start off this with a question. What is this sum? 1 plus a half, plus a quarter, plus an eighth, plus a 16th, plus a 32nd, all the way down infinitely. Let's take a few minutes to discuss with your neighbor, try and like find a way to actually prove that this is true. Even if you already know that the answer should be some number, how do you actually show that this is true? All right, let's have last thoughts. All right, let's bring everyone back. So what answers did we get? 2. How many people said 2? All right, does anyone have a reason why it's 2? Yeah. Mhm. Yeah, that's a good reasoning. The algebraic proof is here. It's kind of ugly. The idea is you double it first, and then if you try to subtract, then all of this stuff, this infinite sequence of numbers cancels out, so you're just left with 2x minus x equals 2. So x equals 2. The way that I like to show it is kind of like this. It's, as you mentioned, every single time you go every single like item is half of the previous. So you get closer and closer to this 2 point here on the right, but never actually reaching it. Each time you make a step, you get halfway towards that 2, but you never reach it. So it gets closer and closer to 2. The total sum ends up being 2. Now, if you multiply everything by 2 to the power of n in this, then what ends up happening is that you end up getting this sequence. 2 to the n plus 2 to the n minus 1. So this 8 is here, this 4 is here. All of that ends up adding to 2 times 2 to the power of n. And then if you just get rid of all of these fractional components, then you end up showing that the sum of the powers of 2 up to 2 to the n is just double 2 to the n minus 1. So 1 plus 2 plus 4 plus 8, that adds up to 15, which is 1 less than the next power of 2 of 16. You like the algebraic proof better? Yeah. It really depends on who you are. You're going to like different types of proofs. It doesn't matter how you like the proof as long as you get kind of that intuition behind what you've about this. Yeah. So this is kind of more the formal way to prove this. You still have to show that like you can subtract an infinite number of things and it works, but we can assume that it's fine for the purpose of this class. Yeah. So these two, the sums of powers of 2, and this one over here, the sum of the first n natural numbers, those are the 2 main summations that we'll be seeing in this class. That's not to say that there aren't other summations. There are. It's just that these are the ones that we kind of expect you to have memorized. So we kind of like to say here, like, there's no magic shortcut for asymptotic analysis. Please repeat after that. There's no magic shortcut. There's no for asymptotic analysis. Yes. In CS 70, you get an entire section that covers half the class on probability. Math 55 is the similar course for the math department, but they don't have the probability section. Instead, they replace that with an entire section on how to do these kinds of summations. So this is an extremely difficult thing to do in general. This isn't a math class, but we are going to kind of expect you to have these 2 memorized. So the sum of the first n natural numbers, that ends up evaluating to the theta n squared. As it turns out, we can generalize this to any arbitrary power. So if you have 1 squared plus 2 squared plus 3 squared up to n squared, then you get theta the n cubed. And is this fun? Okay, yeah. So just arbitrary k, 1 to the power of k plus 2 to the power of k plus 3 to the power of k. That increments the exponent by 1. And those tend to be the cases for most of the polynomials that you'll be seeing. If you have an exponentially growing function, 1 plus 2 plus 4 plus 8 all the way up to plus 2 to the n, that generally evaluates to that last term there because the last term is so big that it's about the same size as everything before it. In this case, it evaluates 2 times 2 to the n minus 1, which is theta of 2 to the n. Similarly, regardless of what the base of the exponent is, you can say something similar as long as k is greater than 1. K to the 0 plus k to the 1 plus k squared plus k cubed up to k to the n is going to be theta of k to the n. The last 2 you might also see in this form. where we say that the last item, instead of being 2 to the n, is just n. And in that case, you just do kind of this substitution, replacing all these 2 to the n's with an n, replacing all of these n's with an k to the n's with an n, and you get the same thing. This is kind of a point of confusion that a lot of students have. They see 1 plus 2 plus 4 plus 8 geometric series, and they say it's theta n. But in this version, it's theta 2 to the n, and they get kind of confused. The reason for that is because this last term in this case is a 2 to the n. The last term in this case is an n. It's always the last term that dominates in an exponentially growing function. Here's kind of just the summation notation version of this. We may or may not show this notation. Just know that this sigma means you take the sum of this function, where you replace I with 1, 2, 3, up to the value of n. Now, there are a bunch of strategies on how you might be able to solve these types of things. You might be able to find an exact sum, write out examples, draw pictures. It really depends on the problem that you're working with. That's why I said that this is a really complicated field. Here is an actual research paper and some diagram that someone used to show their asymptotic runtime of this program. So these kinds of things do end up being used in this kind of like free-form manner. Now, I did say that there's no magic shortcut. I'm about to show you a magic shortcut. So here's something that's come out of scope, but let's take a look at this. When I say that it's like f of I, the sum of values, you end up getting this graph. You kind of get the value of these, and then I made each box a width of 1, so that the total area down here is equal to the total sum of these numbers. For those who've taken 1B, what does this look like? Huh? An integral. Yep. So this is about the integral of from 0 to n of fx dx. Now, this doesn't work for all functions because this isn't quite the same as the integral. You're missing some amount. In effect, what we're doing is we're approximating this Riemann sum by using an integral. Kind of the opposite of what you normally do, where you use the Riemann sum to approximate the integral. Instead, here we're using the integral to approximate the Riemann sum. So it doesn't work in all cases, but this does generally work. That's kind of why if you take the sum from 1 to the k to n to the k, you get n to the k plus 1. Because the integral of x squared is something x cubed. The integral of e to the x is just e to the x itself. You don't need to know this fully. This is just some calculus aside. If you've taken calculus, then it's really cool that it ends up showing up here. Yeah.
What is fx?
In this case, what is f of x? I don't remember what the f of x I chose here is, but it is generally anything. Yeah, it's any function that's continuous, increasing, and doesn't grow too fast. Huh?
How do you get that function in the first place?
How do you get that function in the first place? It depends on the problem. This is just saying if you have a function and you were asked to sum it, then what can you do to solve it? Yeah. We'll talk later about how you actually get those functions, but there's a different part between getting the function, figuring out the summation, and then actually taking that summation and turning it into a small number that you can actually work with. Yeah.
Regarding this, we go back to slide, but I guess k is 0 plus.
Yep.
Those may or may not, in the case where it's theta of n, would the k necessarily be an integer or not?
It doesn't need to be an integer. It just needs to be greater than 1. Yeah. This isn't true here and the other one. In effect, the only reason why we need k greater than 1 is if k is equal to 1, then it's just 1 plus 1 plus 1 plus 1, which does not grow at all. And if it's k less than 1, then it goes down, which is not what we want either. As long as k is greater than 1, it's going to be an exponentially increasing function. And in any exponentially increasing function, the last term is the one that's going to dominate, regardless of about k. It could be 1.1, could be 1.01, could be 1 plus 10 to the power of negative 100. And it'll technically eventually be exponential. It'll take 10 to the 100 times e number of steps to do so, but eventually it'll grow.
I have a question.
Yeah.
For Rayleigh, is that not, what's it, and more times the
We are going to discuss that in a bit. Keep that in mind. I do not believe so. We'll show why in a bit. Now, a lot of these summations are going to be difficult to evaluate. Even these minor changes are going to yield much harder problems, and we'll actually see that a bit later in this class. But you can solve a decent number of them with calculus. We don't expect you to. Mostly what your goal is going to be is to get them down to one of these forms, at which point you can just automatically evaluate them down. In practice, we won't be working with a lot of the raw math, but that's perfectly fine. Uh, Remember that allegory of the cave that we discussed earlier about how you can build something and then you abstract that away. You stop thinking about how you actually work on it under the hood and you now start working on it, right? So imagine you're a car manufacturer. You have to think about how a car works. But then after you build the car, you don't need to worry about how the engine's running. You can just drive it. Yeah. You have a question? Well, yeah. So a theta bound, the question was asking what the difference is between O, omega, and theta. In effect, a theta bound is saying that this function grows the exact same rate as some other function. Now, there's some caveats. It needs to be for sufficiently large n, and we ignore constant factors, but that's effectively what the theta bound is. O bounds and omega bounds are kind of one half of the theta bound. So O bounds are saying that a function grows slower than this. So f of x is O of g of x when g of x grows is larger than f of x. And omega is kind of the opposite. F of x is omega of g of x when g of x is less than f of x. Again, this is with constant factors and for sufficiently large x. But in effect, we kind of think of it as defining what's less than or greater than. So x squared is intuitively less than an x cubed. So x squared is O of x cubed. X squared is theta of x squared because x squared is the same as x squared. So in any case, at this point, we've done all the math to show why everything under the hood works. We can now throw that away and compartmentalize that, and now we can just use our asymptotic tools directly without having to prove them a second time. So from now on, we're going to be looking at actual runtimes of functions, and instead of going all the way down the full proof of things, we're just going to get to the point where we could have used the proofs that we came up with already to show that it's true. So let's take a look at some functions. As a reminder, our goal here, we start off by saying a metric on a program's efficiency. In this case, we'll be doing with runtimes. And since we're dealing with theta bounds, we're not going to care too much about constant factors and things like that. And then we'll classify the resulting function in a theta class. Now, we'll require some summations or special tricks sometimes, but we'll try and work with that. So let's take a look at this one. Find a simple function f of n such that the runtime of this function is theta of n. So we should not have any multiplicative constants added terms. We should have as simple a theta classification as possible. Let's take a few minutes to try and figure out what the runtime is. And feel free to discuss with your neighbor. All right. Let's bring everyone back. How many people said A? It's a constant runtime. How many people said B? It's log n. C, it's n. N log n? N squared? I see. It seems like anyone else picked the other. Sorry. All right. It seems like we're roughly split evenly between theta n and theta n log n. That's fine. Let's try and figure out what it actually is. So the first step I'm going to do in this is I'm going to say that everything in the middle is just 1 unit of work. Why can I say that? Because that amount of stuff does not depend on the value of n. It's just a constant amount of work. I don't care what's going on in there. I just want to say that's 1. So I'll start off with this. And the next thing I'm going to do is I'm going to actually say that this internal thing, 4j equals 0 up to I of 1 unit of work. How many units of work is that total? I units of work. Yeah. I don't know what the value of I is, but this is doing 1 unit of work, I times. So this is I total units of work. And I'm going to try to draw out how much work gets done for each value of n for these small values. So let's start off with I equals 1. When I equals 1, how much work gets done? 1. When I equals 2, how much work gets done? 3. Yeah, because at I equals 1, 2, we go through the loop once for I equals 1, and then once for I equals 2. How about I equals 3? 3. Yeah, still the same because the value n equals 3 doesn't actually add any additional work. At 4, how much work do we get? 7. Yep, because at I equals 4, we now get this this I equals 4 iteration, and now we add an extra 4 units of work. How about for n equals 5? Still 7. N equals 6? 7. N equals 7? 7. So all these print 7 times. And then the next 8 value, yep, 15. And then all the way up to the next power of 2, we get 15, and so on. In effect, the total amount of work that gets done is 1 plus 2 plus 4 up to plus n, as long as n is a power of 2. This is kind of the diagram of like how it would look if we just drew it on a graph. And our goal here is to kind of find a theta bound on this. So just looking at this graph, now that we've done this, how many people say the answer is A? It's constant time. Log n, theta n log n. All right, n squared. All right, it still feels like there's a few people saying n log n. Still seems about even there. Let's see what happens. Well, this is total sum. 1 plus 2 plus 4 plus all the way up to plus n. What does that add up to? Yeah, it's a geometric sum. So you end up getting 1 plus 2 plus 4 plus n. That exponential adds up to the last term, which is a theta of n. So these like peaks, this top point here, those are all equal to theta n. The troughs, these points at the bottom, they're basically the same when n equals 2 to the k minus 1. And if you do the math, you show that it's just equal to theta n as well. It ends up bounding between about n and n plus 1 over 2. So overall, if you have an upper bound that's theta n, and you have a lower bound that's theta n, then your function is growing at theta n overall. Any questions here? All right. Yeah.
So if we make the inner for loop instead of going to I, if we make it go to n, will be in log n then?
If you make this inner for loop go to n instead, then yes, you would have n plus n plus n plus n repeated log n different times, and you'll get n times log n. Yeah, good point here. Yeah, in this case, because each one is like double the previous, only the last term dominates instead of having about the same size for each term. Now, you might be saying that this function doesn't actually exist in reality. Like what kind of function does this kind of thing, right? let's play around with this function a bit. And I'm going to just kind of knead it into a form that you might have seen before. So first step, I'm just going to add theta n total work. I'm just adding this new loop that just does 1 unit of work from 1 to n. That doesn't change the runtime, right? No, theta n plus theta n is still theta n. All right. Next, I'm going to just move this into the for loop. Has this changed the workload? No, I'm just moving stuff around. Next thing, I'm just going to put these in separate functions. That doesn't affect the runtime because I'm just moving things into separate functions. That's going to add some theta of O1 things, but it's still constant time for each iteration of this loop. All right, so this still is theta n, right? And I'm going to now make a slight change and just add a bunch of comments everywhere. This is the same code as before. Uh, what does this look like? Yeah, this looks like an array list code, right? In fact, this is the exact same resizing array list code that we have. And it's specifically resizing with multiplicative resizing. So as it turns out, this is why that geometric resizing factor was better than the linear resizing. If you do n total add lasts to an array list, then your total runtime is theta of n. If you do a similar analysis for additive resizing, you're going to end up getting a theta n squared out there. So over the course of n total add lasts, you're going to get theta n squared with additive resizing, but you're going to get theta n with multiplicative resizing. And as we saw with the summations beforehand, that doesn't depend on the exact factor that you're dealing with. Even if that factor is like 1.01 or 1.1, you're still going to have an exponentially growing thing, and the last term is going to dominate, so your total runtime is theta n. What that means is we divide by n to get an average over all these n operations. Then the add last with multiplicative resizing take theta 1 time total, whereas the additive resizing takes theta n time total. Does that explain what you're confused on?
Oh, wait, so if you add 1 plus 1 plus 1 plus 1 n times what the constant to get n. So if you add like log 1 plus log 2 plus log 3, all log 10.
No, adding log 1 plus log 2 plus log 3 doesn't give you n, but we're not actually doing that. What we're doing is that we're adding 1 plus 2 plus 4 plus 8 up to plus n here. And the reason why is because each time you do a resize, you're just doing theta n total work where n is the size of the array. And that n doubles each time you do a new resize. So the overall effect ends up being that geometric series. I do need to move on, but I can talk with you more after class if you want to discuss further. This ends up being called amortized runtime. A single operation for this type of like array list, it may take longer than any single one, but if you use it over many operations, you end up getting a guarantee of fast runtime. This array list, any single operation could take theta n time, but it's impossible to get those theta n runtime operations one after another, after another, after another. And over the course of n total operations, you're only going to get few enough of them that you get a total runtime of theta n. So amortized runtime in this case gives us a better estimate of how much time it will take to use this function in practice. All right, yeah.
So this rotation, is this saying it's like linear or is it specific or referring to theta 1?
This notation as in the blank amortized? Yeah, amortized here is just saying that if you take the average over a large number of operations, then you're going to get theta 1. So it's not specific to the fact that it's theta 1. It's specific to the fact that we're taking the average over a long time. Amortized kind of means that you just kind of like shave down the like peaks of a really weird growing function to like get an average total. Yeah. So we could have something that takes amortized theta n time, for example, if on average it'll take n units of work. we'll actually show on Wednesday an example of a function that takes amortized inverse Ackermann of n, which is a really, really slow growing function. Yeah. All right. Any other questions before we move on? All right. Let's try another function here. Let's try to find a function f of n such that the runtime here is theta f of n. And let's take a few minutes on this too. All right. Let's bring everyone back. What do people say? What's the runtime of this function? How many people say it's theta 1? Constant time. Log n? N? N squared? 2 to the n? Ah, everyone is saying 2 to the n. Why is that? Yeah, it's tree recursive. Do you have... Were you just raising your hand or was it just a yawn? It seems like just a yawn. All right. Yeah, let's kind of show why this is true. Intuitively, what I would say is that each time you like increase the value of n by 1, you kind of increase the size of this tree by 2, a factor of 2, because you got to make a new copy of this tree a second time. So you kind of double the runtime total. So each time you increase by 1, you double the runtime, and that's the definition of 2 to the n. Another approach, yeah. Huh? If you got rid of the recursive function calls, just one of them. So if you just got rid of one of the recursive function calls so that it's theta of, so it's just f3 of n minus 1, or maybe even 2 times f3 of n minus 1 if you want the same like result. Yeah. Then you'd get a 5, 4, 3, 2, 1, which is just this like left side line. How many items do we have on this side? 5. Each time we increment n by 1, we're going to add one more item to this. And that's kind of like the definition of a linear thing. Yeah, so we'll get a theta n if we only had one of these. But yeah, in effect, if we have these two, then you get this kind of tree structure. And what I'm going to do is I'm going to count the number of these leaves. The idea is that each leaf represents one function call to f3. And the number that I'm putting in here for now is just the value of n for each of those cases. The total runtime is just the total number of leaves because or the total number of nodes, because each node does 1 unit of work. We've got to like set up the function call. We've got to check if n is less than or equal to 1. That takes 1 unit of work total. And if you add up all of the number of nodes, then you'll see that for C of 3, for example, you have one node at the 3 layer, two nodes at the 2 layer, one node, 4 nodes at the 1 layer, and so on. And the idea is over the course of C of n, you're going to get layers. Each layer has double the number of nodes of the previous, and each time you increment n by 1, you add one extra layer that doubles in size as well. Overall, if you add them up, what would the last term of the sequence be? How many people say it's n? How many people say it's 2 to the n? 2 to the n minus 1? 2 to the n minus 1? Okay, how many people say it's a? N. How about b? C? D? E? Seems like a lot of people said D. And yeah, after you have n of these terms, the last term should be 2 to the n minus 1. And what is a simple expression for this function? Yeah, 2 times 2 to the n minus 1 minus 1. Yeah, or total 2 to the n minus 1, which evaluates to what theta class? Theta of 2 to the n. So the work of each call is a constant total, so the runtime should end up being theta of 2 to the n here. Now, I want to make one minor change, just kind of to show, oh yes.
So 2 to the n like a different class than 3 to the n?
Yes, 2 to the n is a different class from 3 to the n because they grow at a much faster rate. Every exponent grows at a different rate, and the larger the base is, the faster it grows. Yeah. You can kind of show this by taking the ratio between 3 to the n and 2 to the n, and that ends up being 1.5 to the n, which grows up to infinity. Yeah. Now, I want to make one slight change to this, just as a way to show how impossibly difficult it is to solve most problems. What is this runtime? I've just changed this n minus 1 to an n minus 2. What do you feel this runtime is? Fibonacci time. Yeah, it is Fibonacci time. What is that? It's somewhere between 1 and 2 to the end. Yeah, but getting an exact number is going to be really tricky. In fact, this is out of scope. This level of math is really difficult. You are correct that it is Fibonacci time. And kind of the reasoning why is because if you look at this total tree, there's Fn total number of yellow nodes, these leaves, because each one contributes 1 to the final sum. And there's Fn minus 1 of these green nodes, because each one combines 2 small items together. Overall, you end up getting theta of Fn, where F is the Fibonacci sequence. So the theta of the nth Fibonacci number. And if you do some Math 55 type shenanigans, you end up showing that this is equal to theta of phi to the n, where phi is 1 plus square root of 5 over 2, or 1.618 approximately. So somehow by changing this from n minus 1 to n minus 2, we ended up at this random theta of 1.618 to the power of n. It is extremely difficult to do this kind of thing in general. There's no magic shortcut for asymptotic analysis. And we can't just say, is there a general trick to this? No. You have to look at each question one by one. Even slight changes might end up yielding completely different results. That's kind of just how math ends up working in most cases. You have
you can focus on for loops, while loops, recursion, functional configuration.
Yeah, there are a few of those things that you can focus on, and they're tricks, but there's no algorithmic solution. There is no one cut and dry way to solve every asymptotic problem, but there are ways to reduce it down to some simple components that you can work on individually, and that's what we're going to be trying to teach you. We'll set up questions so that they can be solved using only those simple things. But there are a lot of questions that you just can't solve. In fact, like there's a question that we made for an exam like a year and a half back that me and Josh were still trying to figure out the answer for. We'll talk about it later. Yeah, it's really cool, but we have not been able to figure out. It's somewhere between n squared and n squared log n. and we have not been able to prove it. It is bugging us. All right. Now I want to finish off today with one algorithm that we're going to be discussing more towards the end of the class, but it's useful to see its asymptotic runtime. Remember how in the testing lecture we discussed a sorting algorithm? The idea of a sorting algorithm is that we have a set of items, and our goal is to sort it in order according to some comparable. Now, for this part, we're going to assume that the comparison method has some properties that allow it to actually work as comparable. Namely, we need to have it so that like x is always less than or equal to x. We need to have it so that either x is less than or equal to y or y is less than or equal to x. You can't have both. You can't have both to be strictly false. And you also need to ensure that some transitive property holds. That's just mainly to show that some sorting exists. We also need to make sure that the comparison method runs in theta 1 time, or we're going to assume that that's true for this case. In effect, in order to compare two integers, it takes a constant amount of time. And we're going to assume that's true for anything that we're comparing here when we're doing our runtime. The way that merge sort works is effectively in order to sort our list, first what we do is we split the list in half. So we cut it into like a first half and we take a second half. And that first half, we're going to sort it recursively. We're to recursively sort the second half. And the idea is once you have two sorted halves, it's easy to combine the two together into a single fully sorted list. Now let's kind of show how this might work. Here's kind of a quick demo of how you might work. Let's imagine that we're calling merge sort on some list, and we've already sorted each of our subhalves. So we have two halves that are sorted. How might we merge these two arrays together? First off, what is the smallest item in the list, in the merged list? 2. How do you know that? Yeah, you just compare 2 and 4. Those are the only two things that could possibly be the smallest item. So we'll move the 2 in. And I'm going to move the pointer over here to show that 2 has already been done. What's the next smallest item? 3. So we move the 3 in. Next. 4. What's next? 5. 6. 7. 8. 10. 11. How much time did this take to finish? Oven. Why oven? Yeah, we do kind of one of these loops. And at each of these steps, each time we added one new item, all we did was one thing. We compared two items, the 6 and the 7. And based on that, we moved the 6 in. We compared the 10 and the 7. And based on that, we moved the 7 in. Each of this takes a constant amount of time independent of the size of the arrays. So this takes theta 1 time per step. After n total steps, it's theta n total. Yes, you had a question?
Just wondering, that's using an array, like data structures.
Yep.
Can you do it with the data structure and how might that affect?
It is an array-like data structure, that is correct. You could do it with an array list too, because all we really need is theta 1 time to add an item into the list. An array list gets us that. We saw that from the link or from the multiplicative resizing version. Yeah.
Still have to sort the two individual lists.
You still do have to sort the two individual lists. And you are doing that recursively. So the runtime of the whole thing isn't just theta n, but the runtime of a single merge step is theta n. Yeah. So the runtime of this is theta n. So let's try and figure out the runtime of this method. So what I'm going to do first is I'm just going to kind of simplify this down. Our runtime, we want it to be in terms of the size of the array. So I'm just going to say the value of n is just whatever the size of x is. And merge is going to take theta n time. So I'm just going to say that that's the same as n units work. If you simplify it down, it kind of looks like this. The sort runtime is equal to, you sort the left half, and that takes sort of n over 2. The right half takes sort of n over 2. And then you do n units of work to do the full merge. What is this runtime? Here's kind of what happens if we draw out the tree for this. Let's take a minute or so to discuss what you believe the runtime of this is. And as a reminder, you don't need to worry too much about the exact details. You just want to get an approximate theta bound. So constant factors, you don't need to worry about too much. All right, let's bring everyone back. What do you think the answer to this is? How many people say it's theta of 1 time? How many people say it's theta log n? Theta n? N log n? N squared? All right, seems like a lot of people are saying n log n. Why do you say it's n log n? Yeah.
Okay, so we have to visit like all the array elements once, but we do this like log n times. We visit all the, we split like log n times, and then we merge log n times. But every time we split, we have to like go for all each array element once. And we're going to merge, so it ends up being n log n.
Yeah, I think that's a good argument. Did you have a
Just like visually looking at the tree structure, you can see that every row is going to add up to n, and we would expect there to be log n rows in the trees.
Mm-hmm. Yeah, I think you're both going down the same idea. The idea is that each of these rows, it takes a total of n over 2 plus n over 2, that's just a total of n. At this next layer, you have 4 of these things that are n over 4, so that adds up to n. You went about it a slightly different way. You said that each item in the list gets looked at and emerged at each of these layers exactly once. But it's effectively the same way to say that each layer as a whole adds a total of n units. How many layers do we have total? Log n. Why is that? Well, we're cutting each array in half until we get down to n equals 1. So that's kind of the number of times we need to have the size of n until we get to 1. And that's the definition of n, or log n. So our total runtime ends up becoming n times log n here. Here's kind of the formal definition or the full proof, but you don't really need to. It just kind of works. All right. So overall, n squared versus n log n, or m squared versus n, that tends to be generally a large difference. But for n log n, it's largely not a big difference. Hopefully this kind of helps. All right.
I think like most analysis
Honestly, they probably need to say that.
Slide. You know how like we were questions today. Oh, you answered this later. Can I show you on here?
Yeah.
Yeah. So yeah, we need to figure out runtime being improved. Here's this slide. Why is this the case? They're like, yeah, this makes sense. But you're talking about this time, right? That's so you have 1 year of work. And when I equals 2, I guess since it's incremented by 2,
If the answer is literally
2, right? I think it would be 2. But like, yes, okay. So then now when I was 3, well, next would be 6, right? So in other words,
well, I is never equal to 3.
Right. You do like 1.
N is 3.
Like for the merge sort, it's
but when n is 3, it just gets past 3.
And compare. That doesn't make any sense.
When n is 3,
right?
The value of I just skips past 3 entirely. It goes from 2 to 4 directly.
Right.
So it never sees when you never get a loop when I equals 3, even if n is equal to 3.
Same thing happens when n is 5 and 6 and 7 because of the way I is incremented. I see.
Yeah.
I mean, then I guess in let's see, like you could do. That was the one I was asking. So even though this is a like, I know I asked that basically if you got rid of like this part, you iterate over n.
Yeah.
Like, but let's say Oh, you can have like
Even though it's recursive,
yeah, I mean you can do it. It's not like
I guess this was 2D.
we're almost
If we got rid of, I guess, this, maybe 4v2,
But it won't be that way because it's recursive. So you don't just get rid of this, you also get rid of this and this.
I think just like yeah,
Right? Yeah.
maybe I didn't see that.
I did not realize you have a touchscreen.
It's okay.
But like, yeah.
Yeah, that's because it's n-1, right? So what if we n-2?
If it was just n-2 with this, then it would. If you had only like one iteration, then it would still be theta n, because you're just decreasing by 2 each time instead. If you did f of m